Hello everyone. In this video I want to answer a lot of the questions that we've got from the previous video, and then talk about the visit that we had with Uncle Murphy, and he decided to bring his favorite cousin Bozo along. We'll discuss that a little bit as well. But anyhow, there's been many questions that have been asked in relation of the last video we did on this custom boring bar that we're making for Keith Rucker. And the thing that probably one of the main questions people are asking is, why aren't you using steel instead of carbide? Well, there's a couple answers for that. One, we happen to have a piece of a broken carbide boring bar laying around, and Adam was kind enough to donate that. And so it would have probably sat around. Whether we would ever use it or not, I don't know. But the more important reason why we went that way with carbide was because on a steel boring bar or threading bar, the amount that you can stick that bar out without problems is only about half of that is carbide. Now here are some of the boring bars that we make and sell right here. This is a 3/8 bar. It's a half-inch bar. These are made out of steel. And so what will happen is, with the steel bar, this being a half-inch diameter, that means I can get roughly, the general rule is I can get about 4 times the stick out. So if I got a half-inch bar, that means I can get this sticking out about 2 inches, cut in soft steel without too much problems. And the further I go past the 2 inch, the likelihood I'm getting up with chatter and harmonic issues, it's going to be a lot more common the further we go out. So with the 3/8 wheel, you can get about 1.5 inches stick out as a general rule. Now here's a carbide boring bar. I made this one, and I'm very reluctant to make these and sell them, because if they're not used right, it's real easy to tear this head off here. Now this has got a special design. I made it just for hard turning. It got a special clamp system. But here's a half-inch diameter, and if I put an insert in there and I was going to cut soft steel, I should be able to get 8 times the stick out. I should be able to stick this thing out 4 inches before I'm going to start running into trouble, compared to 2 inches over there. So getting the rigidities for the cut, we wanted to use carbide, because I got to grind this diameter right here down to 450 thousandths. And the nut that Keith has to make is 2.5 inches long, and so we decided that we should make the bar from the tip to the shoulder and the stick out that he's going to have, we would make that at 2.8 inches. And so for a steel bar, that is going to surpass the 1.5 inch that you have with the stick out. And then with a half-inch bar, yeah, okay, 450, yeah, if it was steel bar, it would be surpassing it, but if it was carbide, it'd be well within that. And plus, when you got a regular boring bar right here, you're cutting with just a small tip. When you're cutting with that threading insert that we have, there's a whole lot more surface that is cutting on there. So this is the main reason why we went with a carbide bar rather than a steel bar. And a lot of people are asking, well, why didn't you just, take your carbide and silver solder, braze, or whatever, another piece of carbide on the end and shape it? Wouldn't that be a lot more easier? Yeah, maybe. There's all kinds of ways. People are talking about burning a slot, or actually cutting a slot in there. Well, I only have 2 diamond wheels, and there's no way I can get a slot in there. I do have some friends that have wire burners, and that would actually be a good wire burn job. And if you had the slot, I think that would work really good, and that'd probably be the strongest in the end, because you can have the bottom and the top. But then when you see, well, what I'm doing, when you got that insert that's 187, there's so little at the bottom over there, even that might not be that great. So anyways, we went with carbide, and we went with this style. The main reason I went with this style with the insert is it already has all the geometry with real nice radiuses and everything all figured out, and I wouldn't have to do that work. But anyways, that's why we went that way. But what we had is, like I say, Uncle Murphy and his cousin Bozo came along, and we had an issue. I had the bar and we'll show footage of me grinding this slot in here using this V block. And I'll show you there's a flat on the bottom side right here. And if I set the flat down, you can see that's running flat. That was my first mistake. What happened was when I had the tip silver soldered in there, and I pulled it out right now, and Kathy will show a picture of that. I was going to grind relief on the heel side, on the relief side of the insert, and I wasn't paying attention, and I ground the cutting inside, so I scrapped out that first insert. And as I did that, and I'm looking at that, and I'm thinking, something's not right. And at my full-time job, I do use the lay-down inserts, but I haven't used them in a while, and we've been cutting threads. I think 10 thread per inch is about the coarsest that we cut. And then we got 12, and we got inserts designed for that. And we never have a problem. I just slap the insert in, and then I start cutting. And I was thinking that I'd have the same thing with all the geometry on this insert. I can just silver solder that on there, and we can take off cutting. And boy, was I wrong. And a couple of our YouTube subscribers pointed this out to me, and we'll talk about that in a minute. But anyhow, what I have to do right now is I have to get this from this flat. I have to cut this pocket, this meat over here. I got to cut at that 15 degrees, and with my 30 there, so we're running a compound angle. And that's where a lot of you people see the templates that I have. Well, I brought a bunch of them home from work, and Kathy's going to show you a still picture. I can't have enough of these either. There's a lot of common angles that I use and I work in. So here's a 75 degree. Here's 15 degree, here's 90 degree. And it works just right that these lay-down tools, at least the ones I use, they have a 15 degree angle relief. So I'll be able to set this up like so on some blocks, and then I'll be able to rotate that flat, and now I got me a real nice 15 degree established, and so it really comes in good and handy for doing things like that. And so when I grind that angle, it'll be good. There's a bigger problem that we have with grinding the relief for the Helix, and I'll get to that in a minute, but the other issue I wanted to talk about was the silver solder. Let me move some of this stuff around. And the flux that you use. There's a lot of controversy. You'll see it all over the internet. And all my life I've been calling this silver solder, and even today, looking at the controversies, some of the comments made, I'm not sure if this is still considered silver solder or not. There seem to be a lot of differings of opinion. All I know, this is the stuff I use between the two pieces of carbide, and that joint is really strong. Now, what you got to do is you got to match. If this is silver solder or whether it's silver braze, you have to match that with the flux you use. And the way you do that, if you come to the back side over here, it'll talk about this. Okay, it's at 1225 degrees. That's the temperature, I believe, the melting point of the silver solder. It becomes liquid at 1370. So it's much higher than the old soft silver solder or soft soldering that you probably generally use. So if I get some flux, I need to look over here, and I can read on the back over here, it says it's chemically active from 800 degrees to 1600 degrees Fahrenheit. So that's within the range here. That's within the range of the melting point there, and so that's how you want to pick your flux with that. Now, one of the most common things I have seen on the internet was that if your melting point is above 800 degrees, they call it silver bronzing. If it's below, and then they would call it silver, silver soldering at that point. Again, now I'm getting even confused on that. But anyhow, there's a lot of controversy. But this is the important part, that your flux matches what you use. And this stuff, this is what I use, and like I showed you, I've made these type of carbide boring bars. Now, the thing why I'm reluctant to make these because one thing I can do is we can take and cut the tips off of these and actually make the screw-on insert to go in there. And I may do some of those bars for myself, but I'm reluctant to sell those because, one, the carbide's extremely expensive, and two, these heads, if you're going in a small diameter hole and you're cutting steel, what will happen, you'll get a bird nest in there, and a lot of times you won't even hear it. You just going in your hole, and then all of a sudden you pull it out and the whole head is gone. Well, a bird nest, and it puts so much pressure that it cracks it off. If you have a good silver solder joint, and that's what I'm going to call this, not knowing if it's the correct term, but for me that's what I called it all my life. Here's one of those boring bar heads that I had. It's a 5/8 diameter. Well, if you got a good joint where it's sticking, you can see this entire carbide broke off and it cracked down the side. It's still stuck and it's holding real good in there. It's very strong. And here's what I did with that silver solder is what I'll do is because when this is round it tends to roll, so I just would heat this wire up and close it in the vise and flatten it out a little bit. And then what you can do, you don't need a whole lot of it, but then you can just take a cutter like this and clip off just a little bit of that, and then you can put your flux on your carbide on both sides, and then you can put that little tiny piece of silver solder in between. You can heat it up with the torch, and when it gets to the melting point, that stuff will just spread out, and it's like liquid. And it's funny, these are two used carbide inserts that I was just practicing on, and I set them like that to begin with, but as soon as it silver solder melt, they would turn and line up to get all the surfaces. It was funny, it's almost like it was magnetic, and so I had to get a screwdriver and kind of hold it and turn it sideways in order to get that to stay in a pattern like that. But this joint right here, I don't know if I can find a way to test it or not. Maybe I'll figure something out and we'll test that on the strength. But I bet that carbide would break before that joint would break. So anyways, that's some of the comment section, some of the controversies over whether this is really silver solder, whether it's silver braze or whatever. I don't know what the correct term is. All I know is this is what I use and this is what works. And the important thing is just getting your flux and your filler material that they in the same temperature range. So anyhow, the biggest issue though that would have been really a mess is I didn't factor in the helix angle of the thread. It's a 4 thread per inch, and that's a very coarse thread. Like I say, about the coarsest that I've worked in is 10. And so we had two guys that helped me out with this. We have Lunky Dog, one of our subscribers, and Russ Kepler. And they talked about the 15 degree, and I did spot that, but yet these guys brought that up. But then Russ Kepler talked about the helix angle of the insert and the relief that needs to be ground into the insert. And so Lunky Dog and Russ both helped me understand and comprehend this. And then when the light bulb finally went on and I figured out what's going on, wow, I am so happy I got good subscribers like these guys that can give me a good education in something. They've been down this road many times. This is the first time I've been down this road working with Acme threads. And so anyhow, when you find someone that's been on that journey before and they're kind enough to hold your hand, never turn them down. So I'm really appreciative of that. So what I'm going to do is I'm going to bring you over to the computer on Fusion 360, and I'm going to show you some of the details of this helix angle and the relief that has to be ground in the insert as a result. Okay, this is just kind of a rough drawing and rough concept. When it comes to Fusion 360, I love it, but when doing some of this helical stuff and some of this fancy drawing, it's kind of hard. So it's a little bit beyond my experience. So basically what I did is I drew this. 875 is going to be our big diameter. 625 will be our small diameter. But what we're going to see is this distance right here on this line is 875. and this would represent the big diameter. This is representing our insert right here. I just roughly figured the point of it at about 100 thousandths, and it might not be exactly that, but it's going to be close. And the thickness of that insert was 188. So here's the insert unaltered. What we have from here to here a quarter inch, from here to here a quarter inch. So we got a 4 thread per inch helix going on over here. And so at 875 with a 4 thread per inch, we have an angle established right here. And if I use just a square tip, now the tip there had some angles, but I think it was very slight. I'd be surprised if it was only 4 or 5 degrees. But anyhow, what would happen is if I tried to cut this without altering that insert, you can see there's a lot of interference right in this area. I would be rubbing with this non-cutting edge, and I would just break the tip off before we got in there. And if I could rub that off, the thread's not going to be even close. So in this case, I would have to alter this relief on that tip like so. But you got to remember, this is at the big diameter. This is 875. If I drop down to where this is 5/8, and we have a quarter inch, on those areas, so that we have our thread per inch. Look at how much more material's got to come out. Look at how much more interference. The angle has increased big time. And so the smaller I go, the more relief I have to have. And if I come back over here, I just drew one at 3 inches, where this is at 3 inches, and we have a quarter inch from here to here. And you can see the difference in the angle. Very slight compared to that, and definitely very slight compared to that. So the smaller the diameter you go, the greater this helix angle becomes. And so that's why I believe this insert that we bought, one reason why the smallest one I can find was a 1/2 inch IC. Those are made for doing some large diameter work. And I'm going to just go in here and edit on the sketch so I can show you the actual dimensions so you can see. So you can see I got from this tip to that tip a quarter inch. I got 100 thousandths in between. I got 3/16 on the tip. But look at a 3-inch diameter that you have. My clearance on this angle coming from this construction line, so this angle right here is 4.8 degrees. I'd have to go probably at least 5.8 degrees in my relief area, and that's if I'm doing a 3-inch. If I come down over here and do the 875, well, look at how much. I went from 4.8 inches, or 4.8 degrees, to 15.9 is what I went to. I'd have to have about a 17-degree relief. When I come over here to the 5/8, look at how this angle has increased. Now it went from about 16 to almost 22, and I'm going to have to grind a relief angle in here, probably at least 23.5, so that I have no interference in there, and that it can cut through that. And by the time you do that, you can see that this insert becomes weak. This area right here, if I remember right, was about 20 thousandths of an inch. You can see here the material that would have to be removed just to match that line. And so what happens is now we're going to have to remove that material at a compound angle. So the difficulty of this job has just increased a lot, and we're going to have to get into some complex compound angle grinding just to show you what we're in for. But I just want to give a big thanks to the subscribers that have been helping me with this, because once you started talking, and like I say, the light bulb went on, I thought, wow, I missed probably one of the most important parts. And in my history with the laydown inserts, all the geometry's correct, and you just pop it in there, and you don't have to do anything else. But again, 10 threads per inch was the smallest I would have to go, and I've never had a problem. If my diameter was big enough, I could probably do the same with this threading, this Acme threading insert. Now, on the other hand, too, the nice thing about it, because you got the relief angle over here, this is what I got to cut out and make relief for. But on this other side, I don't have to worry about it. That can be straight up and down. I don't need to worry about that material there, because this is all clearance already for it. So, one of the other questions that I was asked, well, why don't you do it a different way? And there was many suggestions, many good suggestions, very valid suggestions on why would I do it this way. Well, one, I got into this and I was thinking that the design of the insert tip, I wouldn't have to mess with the geometry, and I was wrong on that. But now my curiosity's got the better part of me. Now I need to go this direction just simply because I want to see if I can do it and if I can make it work. And if I can't make it work, and then at that time I can turn around and we can explore some of the other alternatives on there. But I'm kind of built that way. There's a lot of things I want to see how they work, and we're going to show you some footage, some previous videos where I'm exploring some of the design concepts. Like when I saw Tom Lipton do a video on differential screws. I had never even heard of them, and I found that very fascinating. So I started making some of these differential screws and a measuring instrument or adjusting instrument, so that I can get a very fine resolution adjustment. And so anyways, in the meantime, I thought, hey, I could do another type of adjustment to get fine adjustment, and it's a wedge adjustment. And that one is just something, I don't know if they sell them. This is something that I just thought would work, so I would just try it anyhow. So I did not have any immediate use for it. I thought I would, but I changed, shift gears after talking with another YouTube friend. And anyways, I guess what I'm trying to say over here, I'm going to show you some footage. I make things sometimes without a direct purpose, just so that I can learn from these things. And with these fine adjustment, that one with the wedge, I got the fine adjustment where I can take a 1/4 screw just off the shelf and use that as a push-pull mechanism for this wedge. And the resolution that I could achieve with that was beyond what my amp could even measure. And my amp, the finest resolution per mark is 5/millionths of an inch. And so we're going to show you some footage on that, because that's kind of buried into another video, and I think a lot of people haven't seen it. But this thing is really neat. But I'm just going to show you this footage because I'm going to show you what kind of drives me. Now I got to need to know. And I know curiosity killed the cat, and sometimes that's a bad thing, but that's one of the things that drives me. I just need to know. So all the valid options that you guys have suggested for doing this, we'll probably visit one of those if this doesn't work. But for now, I got to just try this, just see if it works. And that may be a big total failure, and it may be a success. I don't know. The one thing is, it's not with Keith. We're doing this for him, so it's not like he's paying for it and that he's going to come out at a loss on this. Any of the loss will be on me. But like I say, regardless, at this point, this is the direction that I'll be going, just so I can see if it's possible and if it'll work. And plus, by doing all these compound angles and the grinding and the relief of it, is going to be a challenge as well as a learning experience. And maybe it'd be something that a lot of you guys can even find a little bit of value in too. I know that these are kind of things that help me with future projects, because I can use some of these concepts. So anyways, that's what where we're at on this right now. The insert, I had to get another insert, and we should have that tomorrow. And then we can carry on with the build of the boring bar. So thanks for watching. Okay, this is the bottom of the bar. I got the flat on this side, and I already set my insert because it's going to have to be sticking out. The tip of it is going to have to be sticking out this way. So just for reference, I drew a blue line with the direction I got to set this up, so that I got a good reference so I don't grind the angle on backwards. But anyways, we got this flat, and I'm going to indicate this flat in. That way when Keith sets up it'll be easy because this flat will be running parallel with this little notch we're cutting in here, so it gives them a nice reference source to work with. Now, one of the nice things about these squaring blocks and your other tools that I always make my tools in the future, I always make them with the idea that I'll probably be attaching to this a block over here. And here's how it's going to make some of this stuff easy. Because I have a flat going up here, I can take my 90-degree square and I can hold that up against this pin, loosen this up, and get that orientated, and then snug that down a little bit, and that should line me up close, if not perfect. Yeah, look how nice that lined up. So here you got a setup that could take a long time, but because all this stuff works together, it makes short work out of some of this setup. So I'm just going to snug that bar down a little bit more. And anytime you do that, you always want to recheck, make sure nothing moved. We're looking good. Yeah, one of the other things that if some of you guys are making your own tools, these things are so easy to make. This is 45 degree, and 90. And those are some very common angles. And I got many of these, all different sizes with different hole patterns. I like to put holes in the front over here so I can put a screw in there, use it for stop work. Some of them I got the early days with absolutely no holes in them. This one here, it's used very little. It's got a little bit of I don't know, maybe just a real light surface rust on some places. The angle and everything's still good and square, but there's no hole on it. But what we have, we've got a 90 here, we have a 60 here, and a 30 here. Another set of good common angles. Well, that insert that we have is going to be working. You got 3 sides in a triangle, so those would be 120 degrees for a whole circle. So when we're wanting to set this up off of that square, the way I got this set will actually establish the angle so it'll be right in the proper direction. And actually I think I'm going to set it this way. Actually I'm going to have to set it this way, otherwise my guard might not come down low enough on the arm. So I'm going to have to, I would have rather grind it this way so you can see better what's going on, but it looks like I'm going to have to do it in this direction. So what I can do is I can get this surface established, and then I can get this surface established, get that mounted about right where I want. And in this case, because this block is A2, it is magnetic, but not as good as O1 and whatever. I'm going to leave this cold roll block here as a backing just so it doesn't spin. I think I would have been okay without it. But now we have this set up so that when I cut this pocket, I'm at the proper angle in regards to the insert. So if my numbers is right, I've touched off on here, and I got to go 194 thousandths deep. And I'll just go maybe 190 to begin with, and then step over and take that other piece out, and then we'll go from there. Actually, yeah, that's what we'll do. I'm going to end up using coolant, so my cube is going to get full of coolant, but that's fine. I'm going to need it when I'm grinding this carbide. one thing you have to be careful about is the carbide will not handle thermal shock very well. It would be best if I can have my coolant directed where it's always on the carbide, and I could have roughed that out a lot faster, but because my coolant, I was in the grind without the coolant on and coming back in, I just eased it down there. It took me longer to do that, but this wheel is cutting so free that very little heat was going in it, and then it'd come under the coolant, so there was hardly any thermal shock. But if you've got a dull wheel, one that's not cutting free, you want to try to redirect that coolant so it's on the carbide while it's in the cut. So I got to step over now, and we got to take that last little piece off, bring it down to 190, and then we got to work that step into the proper distance. That should be it. At 256, if my math is right, at 256 thousandths, that would put that tip at center line. I want that to ride above center line by about 2 thousandths, so I went, hopefully I got 254. So we're 253 and 7. Yeah, 253 and 7, and again it might be because of the lack of the flatness of the wheel by now, but we're about 253.7, 253.9, and so that will be good. Okay, I just thought of a way that may work. I don't know. I want to test the strength of this solder joint over here, and what I have is I have the point of the top insert that will be hitting on this soft steel, and the point of the bottom insert will be hitting this soft steel. I'm going to apply pressure. I'm going to guess that that tip is going to be breaking way before the solder joint comes out. Now obviously I didn't want to do this with my hard jaws because I'm going to mess them up, so I got just some scrap steel over here that I can work with. So let's see what happens. I got a lot of pressure on there, and something finally, well, you can see it's still joined together, and what happened, it spun out and it embedded in there. But like I say, I put a lot of pressure on there, and it still did not move, and there's no way that the pressure on this boring bar is going to even have 1/10 of the pressure I just applied over here. And you can see that that stuff has just got a super good joint. If it's done right, it's strong, it's powerful. Okay, we're going to do a second take on this because Kathy had some focus problems on there because she was turning her back, afraid that this was going to just blow up.
I was cringing behind the camera just in case something shot at me.
Yeah, so what we're going to do, we got this top insert, and we got the tip of that insert, it's hitting to this wall, or this soft piece of steel. And this soft piece of steel, we got the bottom insert on there. and it will be hitting on there. And so what we're going to try to squeeze this together and see how much pressure that we got to have on there, and see if we can separate that solder joint here. And you can see that there was a lot of pressure on there, just like the first one. I'm going to set this up over there. It spun on there, but I was putting a lot of pressure on there. The first time that we went through, I was putting even a whole lot more pressure, and so I can tell you that with the pressure that I put on even on that, it's at least, I know it's well more than 10 times the pressure we're going to have on the cutting tip on the boring bar. So if the joints are done and prepped right, that silver solder is extremely strong. It is very, very hard. Like I say, in my experience, if it's done right, the carbide breaks before the joint. So anyhow, I hope you enjoyed.